Welcome to the lecture series of digital electronics. Today we will discuss the sequential circuit, synchronous counter. Synchronous, that means the whole circuit is synchronous with each other. Synchronous counters are distinguished from the ripple counter that the clock pulse are applied to all CP inputs is common. CP is common to all. Common input to all flip-flops in the circuit. The common pulse trigger all the flip-flops simultaneously rather than one at a time in a succession as it which we discuss in ripple or asynchronous counter. The decision whether the flip-flop to be complemented or not determined from the value of jk inputs at the time of pulse. If j and k is equal to 0, 0, then no change, and if j and k equal to 1, it will become toggle or complement of the previous output. So a design procedure for any type of synchronous counter was presented in this section which we discussed. And so first we will discuss the binary counter. So this is 4-bit binary counter. Here the 4-bit binary counter synchronous is such that the count enable, if count enable is equal to 1, then and then the enable count will be possible, otherwise the j and k will be 0, 0. If j and k is 0, 0, it is in Riemann stable condition. Okay. Suppose here the flip-flops condition is that the presence value is 0, 1, 1, 1. This is the present value. Okay. 0, 1, 1, 1. And here j and k is count enable, so jk is always 1. If count enable is enable 1, then and then if a1 is equal to 1, see here, if a1 equal to 1, then the next stage will be count complement. If the previous value is 1, then and then the count enable will be 1. So here in each flip-flop, the value of j and k is 1. So in next state all will be complement. So 1, 0 is changed to 1, 1 is changed to 0. So the next count will be 0, 1, 000. Remember that thing, the complement is only possible when and when the previous value of if a1 or a2 or a3 is 1, then and then the present state will be complement. So this is the simple circuit of 4-bit synchronous counter with the help of JK flip-flop. When synchronous, the benefit is that the flip-flop trigger on the negative edge, and this is essential here. It was the with the ripple counter. So the counter could be triggered on the positive edge of pulses. Here 1 to 0. Okay. Remember that this is the only possible 1 to 0. So this circuit is only for positive edge. Next is that the up and down both the thing is that. So here in up and down synchronous counter, the lowest order position is complemented with every pulse. If we flip in any of the position complemented with the pulse provided, all the lower side is equal to 0. For example, suppose the present state of counter is 1100. Suppose here the 1100. Okay, as A1 is always complemented, so A2 is complemented because the present state A1 equal to 0. A3 is complemented because the present state of A2 A1 both are 0, 0. Okay, and A4 is not complemented because the A3 A2 A1 is 100, which is not all zeros condition. A count down binary counter can be constructed in this figure. Here the countdown, if anyone is 1 at a time, if up is 1, then all the JK T flip-flop is that T flip-flop up counter, but the input will be goes into the according to the previous stage. So T flip-flop, we know that the T equal to 1, then the next stage is complement. So suppose here the up equal to 1. So this input is 1, down is 0. So anyone always this flip-flop A1 is always complement, always toggle. Now up is 1, so obviously the upper one AND gate one input is 1, and while below 1 is a 0 always, because the countdown is 0 in the first condition. Now here this is Q dash, so A1 dash, and this is A1, A2 and A2 dash. Here is A3 dash and A3. So if my input is 1100 and up counter is active, so this will become changed to 0 to 1. Now here is 0. The is it this is 0, so 0 and output is 0, so it will be remain same. Okay, A2 is 0 and it will go here. So again it will become 0 0 1 and 0. So this will remain 1. Again this is 1, and but this will become dash is 0. So in up counter direct input is there, while in down counter the previous stage complement of this stage is there. So this will become, it remains same. So next output is 1101. Okay, it is due to this 0, the flip flop of this gate is also 0. Okay, it is complemented here. It is A1. This output is A2 A1. This output is A3 ended A2 ended A1. Means, see here, suppose input is 0011 present state, so the next state is 100. So due to this one, the bit is complemented. When the present input is 111, so next state is due to this 31, complement of the higher bit is possible. Okay, similarly in reverse order for the lower counter, the complement terms will be there. So all the below AND gate will be activated. Above all AND gate is 0. The output of this, because up is 0, down is 1. The output of the all above gate is by default 0, because the one input is 0, that always remains same. Now it is depends on the below lower stage AND gate. So here down is 1. The out present state we are considering, when it is from all the previous stage is 0, then and then it will be complemented. Okay, so let's take the example is that 1 0 0 is the present state and down counter is active. So this 0 here 0 dash, so this is 1, this is 1, output is 1. Again 0, so this will become 1 and this one is transfer here. So all two are 1, so it will become 1. Again 0, so its complement is 1 and this one will be here, so 1, and this is 1 and it is last stage, so we are not worried about that things. Now what happens here in this condition, the input of the T flip flop is 1 1 1 1. So that means the next output is 0, 1 is complement, 0 is 1, 0 is 1, 0 is 1. So all flip flops are input is 1, so all are complemented 0 1 1 1. It is down state. Okay, let's take such an example where only two flip flops are active. Suppose my input is 1010 1010 1 0 1 0. So complement is 1, here complement is 0, here complement is 1, here complement is 0. So first this is always 1. Now 1 is applied here, so 1 1 1. So T is 1. 0 0 is here, so output is 0 and this will become 0. So this flip flop T is equal to 0. Now due to this 0, the here also it is 0, so output is 0. It is whatever the 1 is here, but the output is 0 and T is equal to 0 here. So that means the flip flop 1 to 0 input and this is 1 input 1 input. So what I will do, 0 will complement to 1, but this will not change. So first 2 is not changed, 1 0 1 0, but instead of 1 0 it will become 0 1. Okay, this complement 1 to 0, this complement 0 to 1, and it is -1, down 1. So it is called as a down counter circuit. Now BCD synchronous counter. Whatever in previous case we discussed the BCD asynchronous counter or ripple counter. Synchronous counter, that means the sequence is same, but here if t is increment 1, so input t is require 1. Okay, after that 0 0 1 1, so both are decrement, sorry, both are a complement, so t is equal to require 1. Here only this is there, but now after that it will become 1 0 0 0, so all three are complement here. Okay, then next bit is 1 0 0, first three are remain same, only the last bit is complement. 1 0 1 0, the last bit and second bit is complement. Here only last bit is complement. 0 1 1 0 1 1 0, so now it will become 1 triple 0. So here 1 2 3 4 all are complement. Okay, in this way BCD is up to here, and the last bit after that is 0 0 0 0. So complement first bit, 1 2 middle 2 bit is not complement here. So see, every time TQ is equal to 1, while T2 is alternate. But when Q8 is equal to 0, at that time it is not complement. If Q8 is equal to Q8 bar, we are taking here 1, so it is not complement, else it's complement. So we are taking Q8 bar and then Q1. These two. Okay, Q8 bar and Q1. Q8 bar. Up to here it is Q8 bar. So this will become 0 and Q2. Okay. So let's see here. When it is 1, first A1, second, third and fourth. See here 1, both 0 1 0 1 0 1 0 1. So every time Q8 is 0 and Q1 is 1. So we can say that it's a Q8 bar Q1. Now about the TQ4. TQ4, here we found that only two times its complement. When the first case is here and second case is here. See the sequence in both the case. So first Q8 is 0 and 1. Here also 0 and 1. But this is also 0 and 1 here also. So we cannot be directly say that. So one is the Q8 Q1 and second is that all three is 1. Which two? Q4, Q2 and Q1. Okay. Here all three 1. So due to this one, the second case is that, the first case is this one. Okay, so these two consider state is that. And output Y. Y output is only when the carry is generated. So it is Q8 and Q1, only one is connected here. So we can say that when both are 1, output is 1, else the output is 0. So with the help of T flip-flop, we can design this circuit. It is called as a BCD synchronous counter. Synchronous, that means all flip-flops have a common clock pulse. Okay. Now binary counter with parallel load means sometimes we need the some initial stage output is here. So there is a main three signals count or load. So function table is that if clear is 0, all must be 0. Okay, because the direct clear input is connected here. This is the clear input J and K. So if clear is equal to 1, then clear equal to requires 0 because it is a bubble is shown here. Okay, so when clear is equal to 0, all the flip-flop out will become 0. Second thing is that if clear is equal to 1 and load and count both are 0 0, no change is there, because here the count equal to 0, the AND gate output is 0 and here OR is 0. So first OR gate always 0. Second is the load is 0. Load is 0. So that means the gate of 1. So both are 0, 0. JK is equal to 0, 0 in all conditions. So no change is there. Now, if clear is 1, load is 1. If clear is 1, load is 1, then we can say that here load is 1. So this will become 1. So I1, this will become I1. So J is equal to I1 and K is equal to I1 dash. So we can directly say that if I1 equal to 1, output is 1. If I1 equal to 0, output is 0. So whatever the I is installed into I output A. Okay. So next possibility is that load equal to 0 and count equal to 1. So count equal to 1, it is simply whatever the equation is that the previous stage here A1 is connected. If A1 equal to 1, increment if A1 A2 both are equal to 1, these two gate, it will be increment J and K both are equal to 1. If all three as well as count is enabled, this flip-flop output is enabled. So okay, so it depends on the previous stage J K equal to 1. If all previous outputs are 1. Okay, in this way the binary synchronous counter with parallel load is working. Now the here we have to sometimes it's given mode 6 counter. Mode 6 counter means 0 to 6 or 1 to 7 continuous count is that, or we can say 3 to 6 9, so 9 up to 9 counter. So mode means continuously increment by 1 and total stable stage are 6. So let's say suppose we have to count 0 to 6, so 0 1 2 3 4 5. What we'll do, counter MSI circuit which we previously discussed, count equal to 1, clear equal to 1 and clock pulse is given, input is 0 0. Now what happens, 0 start from 0 0 0 0, then 1 2 3 4 5 and then 0 0 0 0. When 5 is occur, so here 0 1 0 1. Okay, so at that time what happens, 0 1 1 0, sorry, after 5 the next is 6. As 6 is occur, immediately it load to next 0 1 1 0. When this occur, immediately it load what the value, initial value 0. So instead of that thing, momentarily it will change and directly jump to 0 0 0 0 and it will start again. Okay, so 0 1 2 3 4 5, momentarily 6 and suddenly it will be 0. So momentarily unstable condition will be generated in the circuit. Another possibility is that if you do not want to momentarily generate it, what we'll do, if instead of load we can also connect the clear, because the clear is asynchronous circuit. Okay, so inputs have no effect, load equal to 1, count equal to 1 and clear we use it 0 1 1 0. We are take 1 1, it will become 0 because the clear is a negative control signal is that. Okay, another possibility is that suppose we have to start with the 10. 10 means 1 0 1 0 8 4 2 1 and then 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 all 1 and then reset to reset. Okay, so all ones, what we have, all ones are there, then it if next increment will become 0 0 0 0. But we do not want that things. Our aim is that again start with the 10. So what we'll do, carry out will is connected to 1 and 1 0 1 0 initial value, it input to store here. So it will become 4-bit parallel load circuit. Again, another possibility is that 3, 4, 5, 6, 7, 8. 3 start from 0, 0, 1, 1, and then it is increment by 1 in every clock pulse. And after 8, it reset again. So what we do, when A4 is equal to 1 only in this condition, when A4 equal to 1, the load is connected and in next clock pulse, it will become start to count 3. So this is called as a mode 6 counter. Many type of the applications are possible. It depends on the requirement. We can do it as per the statements or problems is given to us.